Yeah.
Feeling ran back to tickle to get a cord. I know that's just fun.
Yeah.
All right. So, did you guys hear me on there?
We can kind of hear you. It's very faint.
Move closer. Now you can hear me?
Echo now. You guys can computer.
Oh, I just got mine completely shut off, basically.
Yes, we can hear you now.
Awesome. All right. Well, we're gonna go ahead and start up here. So this is the PhD defense for Ghada Defense. Just a little introduction. She started in, was it January 2020? January 2020. And came to us from Cairo. And so she's been a fantastic member of the department since then. Just a really hard worker, and it's always exciting to kind of have this day to like show off the work that people have done. So I'll let you do like a little brief bio to introduce yourself, and then we'll start up. But really excited just to show the amount of work that she's done and the quality of work that she's done over the past 4 years. So I will pass it over to you. Just like a quick, what we'll do is she will go through her presentation. It's about 40 minutes or so, and then we'll open it up to whoever has questions from the general audience. After we're finished with that, we'll just excuse everybody other than the committee, and we'll kind of proceed with the exam portion of the day.
Thank you for the introduction. So I graduated in 2017 with a bachelor in civil engineering, and then I did my master's degree, and I finished in 2019. And then during that time, I worked as a teaching and assistant lecturer at the German University in Cairo. And for the past 4 years, I've been working as a teaching assistant and research assistant at the University of Tennessee. And I'm so excited to be presenting my dissertation work, 4-year worth of work, and I couldn't be more excited. So let's start talking about my PhD dissertation topic, which is about enhanced fire tension modeling at the catchment scale and integrated drain mount urban and swim approach. So usually I like to start talking about urbanization. I like to start talking about how with urbanization there is a shift in, or there is an increase in the impervious surfaces, not just the impervious surfaces, but the connectivity between these impervious surfaces. And as a result, we end up having a lot of runoff, more runoff than pre-development or like urbanization, and less infiltration happening within the urban watershed. And this shift in the water balance is also reflected in the response of the receiving stream. So we have like, instead of like a normal response, we would expect to have like higher peaks. We expect bigger volume of water reaching to the stream. All this happening within a short amount of time, less than what it used to be in before urbanization. So here comes the importance, or why we are interested in fine temporal scale modeling in general, because a lot can happen within an hour. So whenever I mention fine temporal scale, I'm talking about 1 minute, I'm talking about 5 minutes, or maybe 10 minutes. time interval. So green infrastructure, bioretention is a widely implemented type of green infrastructure. It promotes infiltration, so it consists of like a depressed storage filled with bioretention media. This bioretention media is engineered soil, promote infiltration. Below this layer, there's underdrain. These underdrain could have like an upturned elbow configuration to form like internal water storage zone, or it can just be straight and it deliver water to the storm sewer. And then on top of the bioretention media, we have vegetation cover and surface storage. So when this surface storage is filled with water, then water starts to overflow. So we're going to be talking a lot about overflow and drainage that is going out from the bioretention cell. And whenever we are studying these bioretention cells, we look at one of three scales. We either look at size scale, or we could be looking at the bigger scale like catchment scale. And initial studies were mostly looking at like field performance of or side scale performance of these bioretention, the volume reduction of water, the pollutant treatment. And then as we move forward in the research, now we are looking more at the catchment scale level and studying like maybe something like paired watershed studies. So there is $1 billion investment going on in these green infrastructure, and having or investing this amount of money should use this money wisely, and we should be using bioretention modeling or green infrastructure in general modeling to plan maybe new bioretention, retrofit existing bioretention, or optimize the design and cost of these practices, and also look at how the local scale or how the site scale to the large watershed scale. So observing or a literature review by one of our attendees, so it shows it identified like 8 characteristics that need to exist in order to do advanced bioretention modeling, out of which could be like internal water storage zone, under drains, considering soil water retention, plant water uptake, and all of this, like we have DrainMod Urban, our model that scored 7 out of these like 8 identified characteristics. So a brief about DrainMod Urban. So it was originally DrainMod, and it's still DrainMod exists, and it's used for agriculture application, and then it was adapted for bioretention application, and it was used to produce the water balance for some sites for bioretention, and eventually to apply it for urban environment to produce hydrographs. Instead of having like this daily output, the model was modified to produce a 1-minute time output, so that we can use this model to produce hydrographs. So this addition will be helpful in urban environment when we are looking at this fine temporal scale. So the model basically, it solves 2 water balance equation, one for the surface, one for the subsurface. It can model all the processes happening within a bioretention. That's why it was originally adapted for this purpose. And when looking at what do we need to do, or how can we, like, given that the model had promising performance in the initial testing, so how can we move forward with this? How can we enhance the bioretention modeling using this model? So number one, and this is always the question when you say that I tested the model for one site, the question is, does it work for other sites? Does it work for other climates? If we have different designs, if we have different condition at the site, will it work for these cases? So number one is additional testing of this model at site scale. And then the second part is about the uncertainty in DrainMod Urban parameterization. As any model, DrainMod Urban requires a number of input parameters. And these input parameters could be soil parameters that are typically measured in the field, or not typically measured, but they can be measured in the field or laboratory tests. And even when we have like measured data, there could also not, these parameters could have some sort of uncertainty even with this in mind. So a sensitivity analysis would be useful for this purpose to identify which are the most sensitive model parameters and how the uncertainty of input parameters can impact the model output. And the third part and the most important part, given the promising performance of this model at site scale, how can we scale this, or how can we use this model and transform it from like site scale to watershed scale? And if like having this model that we think is a comprehensive model and a good model for these bioretention, if it improves the modeling of bioretention at site scale, will this translate into the bigger scale of the watershed and result in better representation of the processes happening within the bigger watershed? So let's start addressing the first objective in chapter 1, which is verifying performance across multiple systems. So original data that was used to test Drainmont Urban, it consisted of like 4 overflow events, and this was not sufficient for model calibration and validation. So we need a data set that contain more overflow events so that we can verify the model performance in this aspect. The second thing, it was tested for one site. So what if we have sites that have different design, maybe different area, different storage, or different bioretention media depth? So here we use a site in Nashville in North Carolina. So it basically consists of 2 bioretention cells grouped together as one, and then 3 other bioretention leading to the same outlet and grouped together as one bioretention. So this configuration, or these 2 bioretention cells, each one had a varying media depth. And given this varying media depth, one is like 60 centimeter, the other is like 90 centimeter. During the construction of these bioretention, there was some clogging issues that happened within the first year of operation. So these clogging issues resulted in excessive overflow happening, and at the same time, the bioretention cells were undersized. So retrofit to these practices was performed, and the end result is that they ended up having like different bioretention area, different ponding depth, and storage volume on the top of these cells. So all in all, given the pre-repair, where the cells were clogged, and then the post-repair where these cells were unclogged, so we end up having like 4 bioretention for testing. For each one of them, we have 1 year worth of data. So we started the calibration of the model. At that point, we didn't have access to the source code, so it was manual calibration. And we split the data into calibration and validation data. And we selected some parameters, and we did like this manual calibration. And we looked at the Nash cliff efficiency and the percent bias output of the model as a performance matrix to determine the best performance for the calibrated model scenario. So first, we always look at hydrographs, which is the model output at, in this case, at 5-minute time interval. And we look at the Nash cliff efficiency. It's ranging from 0.14 to 0.6. Comparing it to the previous study, 0.68, this is still comparable. All the cells, the model had good performance for them, except for one cell which didn't have like hydrograph that we would typically expect because of the clogging condition. And then for overflow, the model performance range between almost 0.5 to 0.9 Nash cliff efficiency. And this is a substantial improvement in the Nash cliff efficiency given the other or the previous model performance. Another part is like visual inspection of hydrographs to see how this is translated in terms of modeling hydrographs. And we can see here the top 2 graphs are for drainage. It shows the measured versus the model, and then the bottom are for overflow. In general, we can see maybe slight like or peak mismatch can be happening, or slight time mismatching that could be happening, but all in all, this is overall a good performance for the model. The other part, which is the volume prediction, because these practices are expected to do volume reduction, so modeling the volume is also like a byproduct of modeling hydrographs, and at the same time having a good volume prediction is still valuable for the model. So comparing this to a previous study for the same sites, we have like 0.77 to 0.9 and 0.59 to 0.96. So how can we evaluate these numbers? We look at SCAT scale, which says that the nested flip above 0.6 is a good performance at daily output, and a nested flip of 0.75 is considered excellent performance. So it ranged from like good to excellent performance. And then here we are plotting the simulated versus the measured volume for drainage on the top, and then the bottom for overflow, and the one-to-one lines. So it shows if these values are approaching, if the simulated is approaching the one-to-one line, then it's probably matching the measured drainage or the measured overflow. And then also we did the same for peak flow. So the top are showing like the simulated drainage peak, and the bottom are showing like the simulated versus the measured overflow peaks. The only thing that we can notice here is that for the pre-repair cells for drainage, we introduced a clogging layer, and this clogging layer resulted in like a plateau effect, or like the model predicting the same peak for almost most of the events as a result of this clogging layer. But overall, other than that, the model performance is still good. So in general, in this chapter, we looked at the site scale performance of DrainMap Urban. We looked at overflow, we looked at drainage. The results from the overflow support the limited amount of testing performed previously for the model. And at the same time, we looked at like different varying media depth and varying surface storage and varying bioretention area. So all in all, we think that the model is showing promising or good performance in terms of modeling bioretention at site scale, especially when they are performing under normal condition of no clogging. Okay, so moving on to the other objective, the second objective, which is related to comprehensive sensitivity analysis. So here we are trying to determine what are the most influential, or what is the ranking of the parameter according to like the most influential model input, so that we can maybe prioritize these input in calibration or in parameterization of the model. And then we also identify the impact of uncertain parameters on the model output, especially if we are using the model in uncalibrated state. This would be valuable to see how much a parameter or an input parameter is sensitive and the output is affected by this input parameter. So for this study, we used one of the bioretention cells, the 60 centimeter post-repair cell for this purpose. First, we identified which site, and then we start by selecting the parameters that we're going to be addressing in the sensitivity analysis. We ended up selecting 10 parameters, mostly soil parameters related to soil layer conductivities, seepage parameters, and we had like 2 other design parameters, and most importantly, the soil water characteristic curve, which is considered one of the most challenging input parameters to the model. And once we have identified these parameters, we came up with a range of acceptable range for these parameters from literature. And we did generate like 1 at a time samples. So we ended up running the model 1,000 simulation for each of the 10 input parameters by fixing all the other parameters and varying a single parameter at a time within the acceptable range. So this is the first part of the sensitivity analysis. The second part is we used Sobel sensitivity analysis, which is a variance-based sensitivity analysis. So we generated a Sobel sequence of like a number of samples. We kept increasing the number of samples until we are sure that we have reached conversions of the model. So we ended up having like 1,024 samples, which results in a total of almost 22,000 model simulation. And what kind of output are we looking at in the model? So this is, these are the output that we're going to be considering in the sensitivity analysis. First, the volume related output, the annual drainage ratio, which is the annual drainage volume divided by the annual rainfall, and the same for overflow. And then as a representative of the hydrographs, we looked at the peak flow and the flow frequency above a certain threshold. In this case, it's the 95th percentile flow. And then we also considered a performance matrix, which is the Nash cyclic efficiency, both for overflow, for drainage, for daily output, and for the 5-minute output of the model. So the main idea of the SOHO sensitivity analysis is that it decomposes the output variance into the contribution of individual model parameters. So given the sample that we are studying, so there is like a total variance for all the model output. And then we have the first order index, which is the ratio between the first order or the variation or the variance of the first order model output divided by the total variance. And then the second order is just the variance from parameters interaction divided by the total variance of the model. And then the total order is the summation of all the orders for a single parameter. So here we start looking at the volume sensitivity analysis. We have the annual drainage and the annual overflow. So the annual drainage was most sensitive. So these like sensitivity indices should range from 0 to 1 if the sensitivity analysis converged well. And in this case, we have like 3 seepage parameters on the figure on the left side. 3 seepage parameters were the most influential for drainage. And then for overflow, we had the saturated conductivity of the bioretention layer, the ponding depth, and the drainage coefficient as the most influential parameters. But that does not mean that other parameters are not sensitive. But these are like, in terms of ranking, these are the most sensitive. And in overflow, we observe some second order interaction, which means that there is some sort of interaction happening within model parameters that is impacting the model output. So here, each graph of this is showing the results of one at a time sensitivity analysis. So each graph is generated by computing the cumulative drainage or overflow volume when fixing all the model input parameters and varying just a single parameter. So here we're showing this for 9 parameters for drainage and overflow. The gray zone area is all the possible outputs when we are varying this model input parameter. So you can see in drainage, the seepage parameters are like E and F are the most like one that can alter the cumulative volume prediction, but other parameters are still impacting the volume prediction. When there's like overlapping between these lines, it means that this parameter is not impacting the volume prediction that much. And same for overflow, we could see that the same parameters identified by the SOHO sensitivity are the ones that are sensitive in terms of volume prediction. And then when it comes to hydrograph sensitivity analysis, and here hydrograph is like 5-minute output of the model, we can see that the same seepage parameters are still sensitive in addition to 2 other parameters in case of high drainage, which are like the saturated conductivity of bioretention and the drainage coefficient. And then for overflow, we had the same 3 parameters that are the most sensitive in terms of hydrograph volume are also sensitive for overflow hydrographs. Here, this is the same concept, but in this case, we are plotting the measured versus all the simulated drainage hydrograph and overflow hydrograph for a sample event for each of which. And you can see the bigger the gray zone, it means that this parameter can impact the output or the hydrograph greatly. Moving on to this part of the results, so the figure on the right side, it shows the second order interaction. So the darker it is, it means that there is some interaction happening between the parameters. So we can notice that in drainage and figure B, and drainage daily output, there's like some seepage parameters having high second order interaction. For overflow, we can see also that the KSAT2, which is the bioretention media conductivity, is interacting with almost all the other parameters. So the way we interpret this is that if we are like having second order interaction, mean that these parameters should be calibrated altogether during model calibration. The final part is like sensitivity categories. So we used the approach used in a previous study and adapted for our study to categorize model input into highly sensitive, moderately sensitive model input parameters, and sensitive because all the 10 parameters were actually sensitive model input parameters, but they just varied in their sensitivity according to the outcome of the model, whether it's drainage or overflow, and according to the time scale, whether it's a 5-minute or a daily time scale. So all in all, this sensitivity analysis, we find out that all 10 model parameters are sensitive. This is not a negative thing. This is a positive thing because if you are interested in studying the impact of these parameters on the model in general, in the design configuration, the model would be interacting, it will be producing, results. And the second thing is that we talked about how the level of model sensitivity is function of the model output, whether it's overflow or drainage, and function of the time step. And we ended up having these sensitivity categories. So these parameters shall be prioritized in model calibration in general. So now we can move to my favorite part of this dissertation, which is a coupled drain mod, urban, and swim model. So the whole idea is that we are interested in coupling drain mod, urban, and swim. I will elaborate on this more. And we're interested to test different scenarios of the couple model calibration and how presenting or representing bioretention at catchment scale would improve the modeling in general when we are using swim drain mod. Okay, so first of all, the study area that we've used is from city of Columbus, Ohio. So it's a residential area, almost 12 acres. It has 3 bioretention cells marked with stars, and their total area is almost 1,000 meters square. There's like this media composition, 80 to 90% loamy sand and 2 to 5% organic matter by weight. And this is like the cross section of these bioretention cells. So here we are interested in coupling drain mod and swim. The reason behind that is drain mod urban is a good size scale model for bioretention. And swim is a catchment scale model, and it has routing capabilities which could be useful so that we can study the impact of having multiple bioretention at the catchment scale. So in order to make this coupling possible, so swim is written in C, while drain mod urban is written in Fortran in the 70s. Swim, luckily, it has like PySwim, which is a Python wrapper. So that was a good thing so that we can have like this Python environment to run this couple model. Drain mod urban had a Fortran. It was written in Fortran, so we needed to develop like a Python interface for the whole model so that we can make this coupling possible. And once we have these models coupled, the main idea is that we're going to model the whole catchment using swim and then get the inflow to the bioretention cells and do some like use the Python interface for data processing and matching the time steps, and then taking this out input and feed it to drain mod as inflow to the bioretention. Run drain mod urban. Once we run it, we get the outflow from these bioretention. We can feed it back to the outlet node in swim. So this is in the most simplistic way how this coupled swim drain mod urban would be working. To make it more customized for our case, so I mentioned that we have 3 bioretention cells. In this case, the subcatchments that are draining to each bioretention are color coded. However, we have like the east bioretention cell. It ends up draining eventually to the central bioretention cell. So this added the level of complexity. At the beginning, we were supposed to run swim model twice, once for getting the inflow and once for feeding back the outflow from bioretention, but now we have to run the model 3 times. So the first time we run the model would be for extracting the inflow to the upstream east and south bioretention cell. And once we get this inflow, we're gonna run drain mod urban. We're gonna get the outflow from drain mod urban, feed it to the outlet node at the swim model, remove all the subcatchments because we are already accounting for this inflow using drain mod output, feeding it to the outlet node, and then run the second swim model. So in this case, we are interested in getting the inflow to the bioretention cell, which is the central one. And finally, do the same for this bioretention cell. So we're gonna be running drain mod urban and then feeding the outflow of this central bioretention cell to the outlet node and run the final like swim model. So in order to calibrate the model, we split the monitoring data into 2 periods, one for calibration for events and another for validation, which had like 48 events. We ended up calibrating 7 swim input parameters, including subcatchment width, manning roughness of subcatchment, surface and depth of depression storage, infiltration parameters, and we used like the sensitivity radio tuning tool in PC Swim for this purpose. For drain mod urban, we ended up calibrating 6 model parameters, including the connectivity of the 2 top layers, the mulch and bioretention layer, the surface bonding, and some 3 seepage parameters. So in this part, we are interested in looking first at the model performance under different calibration scenarios. The first scenario is like the uncalibrated model, because using a model in the uncalibrated state this is what's going to happen if we are in the planning phase or if we don't have field data for calibration. So we needed to understand how this model would perform when it's uncalibrated. The second scenario is like when both drain mod urban and swim are calibrated. The third scenario and the fourth are when either swim or drain mod is calibrated. So we're looking at the hydrograph output. We're looking at the maximum flow, mean flow, and volumes. So if we are looking at the hydrographs, we see that the calibrated model for both like swim and drain mod urban had the best performance over the 4 model scenarios. And when it comes to volume, the swim calibrated one had the best volume prediction. But all in all, the volume prediction exceeded 0.75 for all cases, including the uncalibrated model state, which is considered excellent performance in terms of modeling events or daily output from the model. Here we are plotting the measured versus the simulated under 4 calibration scenarios. One is like the top the top 3 plots are showing like 3 events for the uncalibrated versus the calibrated state, and versus also the observed. And then we have at the bottom the swim calibrated, the drain mod urban calibrated output of the model. And then we also plotted like the simulated versus the measured peak flow, mean flow, and total volume. You can see that the differences would be visible at higher or bigger peaks and bigger volumes. And this is attributed between the calibrated and uncalibrated model state, because this is how the Nassau-Cliff efficiency would function. It will favor bigger, or it will favor peaks in general and in the calibration. So it was obvious in this model output. The second part is looking at how modeling or representing bioretention at the catchment scale would result in a model performance. So first we have like 3 scenarios, and for each scenario we have like, or 3 models, and for each model we have the uncalibrated and the calibrated state. The first one is swim, when no LID, no bioretention is represented. We are just modeling the full catchment, and we are not doing any special or explicit representation of bioretention. The second scenario is when we add bioretention as LID module in the swim model. And the third scenario is when we are coupling swim and drain mod and representing all bioretention using drain mod urban. So in general, each of the calibrated state of the model outperform the uncalibrated state for each of the 3 cases. But most importantly, when we look at the hydrograph Nash cyclic efficiency, we find that the couple swim and drain mod urban had the highest Nash cyclic efficiency, which is translated to better performance of the model. And also for the volumes, we ended up having like 0.97, and as I mentioned before, any Nash cyclic efficiency above 0.75 per volume, this is an excellent performance of the model. So all in all, in terms of hydrograph and volumes, swim drain mod urban was better. In terms of peak prediction, swim LED model outperforms the swim drain mod urban model. So if there's something, or there's a take-home message from this, is that in general, representing bioretention and the watershed scale model improved the model performance. And in general, representing these bioretention using the couple model added to the improvement of the model, or improve the model performance beyond that point. So here we have the same hydrograph for each of the 6 cases. The 3 top are the uncalibrated state. The 3 at the bottom are in the calibrated state. And we can see how the Nash cyclic efficiency is varying according, for this specific event is varying according to what model we've used. And for the swim drain mod calibrated model, it was the highest. Swim LID calibrated was also comparable at a Nash cyclic efficiency equal 0.8. Here we're showing also the simulated versus the measured peak flow, total volumes, and mu flow for all these 3 cases. So also the difference in general between the uncalibrated and calibrated will be more pronounced, or like bigger event volumes are most impacted by any kind of calibration in general. So this study specifically coupled swim and drain mod urban. So now instead of having like drain mod urban, which is a side scale, now it's like a catchment scale model. And now we can use it to represent more than one bioretention. We looked at different calibration scenarios. So the outcome is that calibrating drain mod only had limited impact on the overall model performance compared to calibrating swim component of the model. And this is obvious given the bigger scale that swim model component is representing compared to bioretention, which is like smaller in scale. And then the combined calibration of swim and drain mod urban, of course, resulted in the best performance. This would come at the cost of like computational time and computational effort in general. And still, which is important part, is that the uncalibrated swim drain mod urban model performed reasonably well. So it could mean for the future that using the uncalibrated model could be a good option when no field data is available. So also the study demonstrated the importance of bioretention representation at the catchment scale. So incorporating bioretention or adding them in the representation of catchment scale significantly improved the accuracy of the watershed model. And the coupled drain mod urban outperformed swim in hydrographs and volume prediction. Meanwhile, swim outperformed in terms of like peak prediction. However, the coupled model is showing promising performance in modeling bioretention at catchment scale with and without calibration. So all in all, the whole dissertation looked at drain mod. It was tested at site scale and at catchment scale. In terms of site scale, the performance is strong, and it was able to model bioretention at different, like multiple sites, having like varying characteristics, depth, ponding volume, and clogging and unclogging condition. And the couple model in general was used for catchment scale, and it showed promising performance. And at the same time, we've been evaluating drain mod at different time scales. We are looking at the fine temporal scale, which is relevant in urban environment where there is like a rapid response that we are trying to model like the hydrographs with good accuracy for drainage and overflow. At the course time scale or the daily time scale, it could be useful for volume reduction application. And the good thing is that if you calibrate drain mod urban for fine temporal scale, it will result in good volume prediction. So it eliminates the need for like calibrating the model specifically for volumes. And also we've discussed this model sensitivity analysis, categorize the parameters into like different categories in terms of sensitivity, highly sensitive parameters to be prioritized, model output is shown within the acceptable range for each parameter. So it shows how uncertain this parameter can result in like output that is uncertain. And in general, if there's something with like a take-home message is that improved site scale modeling of bioretention using drain mod at site scale translate to better estimation of watershed scale output when used in swim drain mod urban. So what could be done next for site scale? I don't think we have tested drain mod urban for enough sites with internal water storage zone. So this could be opportunity in the future. The second thing is the idea of transferability. So every time you mention that you calibrated the model, you get the question of, okay, does that work for other model, or how can we use these calibration parameters and use it for other sites if we don't have data for this purpose or for calibration? The other part is like the model in general uses like, which is applicable for all models, use like constant infiltration parameters, even though like soil parameters could vary according to the season. So, and some other parameters could be, you know, dynamic. They are not constant all over the simulation time. So this is also another opportunity. For catchment scale modeling of bioretention using like swim drain mod urban. So maybe a sensitivity analysis for this part of the model, taking into consideration the ratio between the drainage area and the bioretention area, and seeing how this would scale up a decatchment scale. Maybe additional testing would always be useful for sites with additional or more bioretention cells. If we are modeling a catchment scale that has a bunch of bioretention cells, maybe we would need to aggregate them, or maybe discretization would be a topic that we'd be interested in to look at when we are modeling a catchment with bigger number of bioretention cells. So all in all, I would like to thank everyone who's attending today. I'd like to thank my committee members, Dr. John Hathaway, for being the best advisor I could ever wish for. Dr. John Schwartz, I've taken so many classes with him. Dr. Andrea Ludwig, I've been to many field trips with her, and Dr. Ryan Winston provided us with the most important like data that we've used to test the coupled model. Thank you for being my committee. I would like to thank Dr. Whitney Lesenby. She's taught me how to use drain mod urban, and she passed the project to me, and she shared her ideas, and she always shares her like feedback. I'd like to thank HRG Group. I hope you get well soon, everybody who's not here today. And the previous members who are also attending, I really appreciate that you're attending today. I would like to thank my friends who are attending here today, Shide and Ala and Najwa, and also my friend Michael, he has been my mentor. And finally, I would love to thank my family for being part of this journey. And yeah, thank you all. Thank you so much.
All right. Hopefully you got a little bit of reverb, but not too bad. Great. So we'll just kind of open up for anyone who has questions. If you, I'm kind of monitoring the chat. You can feel free to enter it on there, or you can just unmute. That's also fine. If anyone has any questions for Ghada.
Yeah, I have a question. Hi everyone, it's Whitney Listenby. I guess I was just thinking, like, getting to this part of
Okay, so again. So what was your question? I couldn't hear. Sorry.
oh yeah, I got muted, I think. Can you hear me now?
So usually there's like a manual that provide guidance for bar structure. They just tell you it's very rough. Like it will tell you the bar retention media depth, what is a good range for this. You can determine according to the size of the area of the bar retention. And you're treating the first inch of rainfall usually with these bar retention. So this is like the variation in the media depth. The surface storage also, it's gonna give you a range of 6.5 inches. So I'm gonna speak within this range. So like the design in general, it's very rough, but they could be different. And they could have like different sizes according to how much water you're expected to use for attention to.
Can you hear me?
Yes, I can hear.
Perfect. No worries. So I guess I was thinking, like, everything about your combined swim drain mod urban catchment model is super cool. Definitely awesome to be able to move forward with seeing how to understand these bioretention better at a catchment scale. And I was thinking a lot of the other swim studies that have looked at bioretention have been focused primarily on, runoff reduction, right? Because that's the best that you can get with swim right now, is looking at volume change and such. But using this hydrograph approach with the combined drain mod urban model, like what other benefits do you think that these users of swim could get out of using this coupled model, thinking about how using hydrographs might kind of enhance the usability of the model beyond just these simple runoff reduction techniques that are used now?
Okay. Okay. I think she's asking that so the benefit of like typically swim models used for volume reduction. So we're looking at how much volume reduction these bar reduction would result in. However, what is the benefit of modeling like bar retention at catchment scale at like this fine campground scale, like 5 minutes and 1 minute output? So what could we potentially do with this kind of output? So my answer is I think right now there's like ongoing effort, and I think one of our team member was looking at like column studies for bioretention and looking at like the moisture and using like sensors and control to maybe open the gate at some point to drain water or something like that. So maybe in the future, if we are gonna get into this level of complexity for these kind of practices and having like some sort of control over these practices, this could be an option so that according to what is the inflow to these bioretention, we can control the outlet. Just like we're doing this, I think, with ponds. There's like a pond study that is going on right now, and they're using like machine learning for this purpose. So if something similar you come up with for bioretention, this could be another thing. I could think of like if we are having like a certain like objective for the flow. Maybe we don't want the flow to exceed a certain peak because this would result in like erosion or something happening to the stream. So maybe this could also be something that we look at this scale. I don't know for now if you're be interesting to look at like base flow and how these practices in general are interacting and affecting in general the base flow, how like where's this water that is seeped out of these cells are going. So this could also something that we could look at.
Yeah, actually the base flow component's really interesting because I think that DrainMod probably has better groundwater parameters than what Swim has used before. So that would be an improvement there too. Cool. Interesting. Thank you.
Thank you. I don't know exactly what all of based on modeling, what we say are what we say are their properties are okay. So in terms of like the most important parameters, I think they are the soil water retention curve and the saturated conductivity of the bioretention layer because it was the most sensitive one. The soil water retention curve might not be